Hello, this is Dr. Joe Trout from Stockton University, and today we're going to talk about what constitutes science. So as you know, in this course, we're going to evaluate how the assessments are done with STEM students. And STEM stands for science, technology, engineering, and mathematics. And it actually represents an interdisciplinary approach to education. And it integrates these four core disciplines and emphasizes critical thinking and problem solving, creativity, and collaboration. So we should talk about just what is science. So there's several definitions, good definitions for science. One of them comes from Wikipedia, and it says science is a rigorous, systematic endeavor that builds and organizes knowledge in the form of testable explanations and predictions about the world. And it defines that there's three major branches of science: natural science, which is physics, chemistry, and biology, which studies the physical world; social sciences; and formal sciences. So there's logic, mathematics, and theoretical computer science, which study the formal systems governed by axioms and rules. A second definition comes from dictionary.com, and it says it's a branch of knowledge or dealing or study dealing with a body of facts or truths systematically arranged and showing the operation of general laws. The Science Council went a little further, and they said science is the pursuit and application of knowledge and understanding of the natural and social world following a systematic methodology based on evidence. And the scientific methodology, they go on to define, has to have objective observations. So it measures data and it possibly, although not necessarily, uses mathematics as a tool. It collects evidence and it experiments or makes observations as benchmarks for testing hypotheses. This idea of experimentation or observation comes from the fact that, for instance, astronomy is a perfectly good science, and yet it's a little hard to do experiments. And prior to the advent of computers, it was really hard to do experiments. Now, at least in science and astronomy, we can do numerical experiments on a computer. For instance, we can go ahead and come up with a concept or a theory on how stars are formed, and we can run computer models to see to experiment with this concept. But there's no way we can go into the lab and make a little star or something like that. There's also induction. So there's reasoning to establish general rules or conclusions that are drawn from facts or examples. And repetition. So we have to constantly test our theories and keep experiment with them. And so this brings in the repetition. We need critical analysis when we look at the data, and we need verification and testing. So this is a critical exposure to scrutiny, peer review, and assessment. Let's see what ChatGPT has to say. So ChatGPT, in its wordy answers, as usual, says that science is a systematic enterprise that seeks to acquire knowledge about the natural world through observation, experimentation, and logical reasoning. And it goes on to say that it's both a body of knowledge and a process for discovering and understanding the world around us. So it says that science aims to explain the natural phenomena by formulating hypotheses, testing them through experiments, and then refining our understanding based on the evidence gathered. Some of the key features of science is that there's empirical evidence, so it's based on observations and experimentation. It's also an objective approach, so we want to minimize bias and try to have our theories rely just on facts. There's also a systematic methodology, so it follows the scientific method. And the results have to be consistent, so they have to be reproducible. Also, our hypotheses have to be testable. And there has to be a way that can prove they're false if they are false. They also have to be progressive in nature, so they build on the existing knowledge. And it has to be open to revision, so theories can be revised based on the new evidence. So digging in a little deeper, if we look at the empirical evidence, so scientific knowledge should be based on evidence that's obtained through observation and experimentation. And the evidence has to be able to be measured and tested and verified by others. We also have to have an objective approach. So as scientists, we try to be as objective as possible. So we try to minimize bias and personal beliefs when conducting our research and interpreting the results. We also need a systematic methodology. So scientists try to follow as much as possible the scientific method. So this invokes observations, forms hypotheses, tests these hypotheses through experimentation, and then analyze the data and draws conclusions. It also has to be reproducible. So scientific findings should be reproducible by independent researchers. And this is very important. So one of the reasons to publish things are so that other scientists can read it and try to reproduce it and see if they get the same results. As we said, there has to be falsifiability, right? So it has to be able to be tested and potentially found to be false. And this means that there must be a way to determine or demonstrate that a hypothesis is false if it is indeed false. So this is crucial for distinguishing scientific claims from non-scientific ones. It's also progressive in nature. So scientists is a cumulative process, and new discoveries are built upon existing knowledge. So leading to a continuous refinement and an expansion of our understanding of the natural world. It also has to be open to revision. So scientific theories are subject to revision or rejection based on new evidence. And we can't consider any scientific theory to be absolute or final. It has to always be open to scrutiny and modification if necessary. So whenever we publish papers and publish our results of experiments and our theories and our research, we use the IMRAD scientific format. So this starts with I is introduction, M is methods and materials, R is results, and D is discussion. So if you look at the introduction, what we have to do is provide a research question and then explain why it's important, why people should go on reading our research. And we have to review the background and known information of the topic. So as we said, science should be progressive and it should be build on what we have and what we know already. So if we do some research and we're publishing the results, we should give the background of what was already done before we started our experiment or our research. We also have to look at the methods, and we describe the methods for gathering the information. And the reason for this is so that if somebody else wants to go and repeat our experiment, they can. So in the papers we publish, we try to give people enough information that they can repeat our experiment or our research and get the same result, and hopefully get the same results. Then there's a results section where we just describe what we found in our research. And then at the end, there's a discussion session where we would discuss what the results mean and how they advance science, or possibly what went wrong with our research. So there's different fields of science. By the way, when I get something from ChatGPT, and it's a useful tool, and you should use it whenever it's appropriate, and not use it to do things like write papers for you or write lab reports. And you should always verify its information. However, sometimes it is easy to use to find certain pieces of information, and as long as you verify that that information is correct, it's acceptable in my classes to use ChatGPT when possible, when appropriate. So anyway, this comes from ChatGPT, and whenever you see this little symbol on the side, that will signify that it came from ChatGPT. So first, look at physics, right? So physics is a branch of science that deals with the study of matter, energy, and the fundamental forces of nature. And by these fundamental forces, we usually talk about gravity, electromagnetism, and the nuclear interaction, so the strong and the weak force. And physics seeks to understand how the universe behaves and at its most basic level, and to uncover the fundamental principles governing its behavior. So we like to study matter and energy and the interaction between the two, right? So these include particles and atoms and molecules and their behavior. We like to look at the laws of motion. So we have Newton's laws of motion. We also have Kepler's 3 laws that talk about the motion of the planets and other objects in our universe. We also like to talk about electromagnetism. That's the study of electricity and magnetic fields. Thermodynamics, which explores the transfer of heat, and heat is another form of energy. There's quantum mechanics. This investigates the behavior of particles at the smallest scale, so smaller than atoms or protons or neutrons. Relativity, so this examines the nature of space and time, and it's described by Einstein's theories of special and general relativity. And then there's astrophysics and cosmology. So astrophysics studies explores the universe in the largest scales and includes the origin, structures, and the evolution of galaxies and stars and the universe as a whole. Also, part of the STEM fields is chemistry. And chemistry is the study of matter and its properties, composition, structures, and changes it undergoes during chemical reaction. So it explores the interactions between atoms and molecules that form the basis of all substances in the universe. So chemists like to look at the atomic structure and examine the composition and arrangement of atoms. And they like to look at chemical bonding and see how these atoms form bonds such as covalent and ionic and metallic bonds. And we also like to look what happens when we put two chemicals together, how they react. Stereochemistry deals with the quantitative relationship between reactants and products in chemical reactions. It also explores the states of matter. So we have solid and fluid. So fluids include liquids and gases, and then a special type of matter known as plasma. And it looks like to see the phase transition between these states. Chemists also, like physicists, study thermodynamics, but they examine the transfer and transformation of energy in chemical reactions and processes. There's this also organic and inorganic chemistry. So this studies the structure and property and reactions of organic compounds, that they're ones that contain carbon, and inorganic compounds, compounds that don't contain carbon. Then there's biochemistry that investigates the chemical processes and substances occurring within living organisms. We also have biology. So biology studies the living organisms and their interactions with each other and their environment. And there's a wide range of topics covered in biology, right? From structures and functions of molecules within cells to the behavior and ecology of an entire ecosystem, like, for instance, our pine barrens or our ocean waters that are around Stockton. So some of the things they study: cellular structure and function, genetics and heredity, evolution and how things have evolved, ecology. So this explores the interaction between organisms and their environment, physiology. So that examines the functions and processes of living organisms, such as respiration and circulation, digestion and reproduction. Anatomy and morphology studies the structure and forms of organisms. And taxonomy and classification, right? So classifies and categorizes organisms. And microbiology investigates microorganisms such as bacteria and viruses and fungi, and looks at their role in health and disease in the ecosystem. Mathematics is the systematic study of numbers and quantities, shapes, structures, and patterns, as well as the relationship between them. So some of the things that mathematics covers is arithmetic, right? And this is just deals with basic operations and properties of numbers, right? Like addition and subtraction and multiplication and division. Then algebra studies mathematical symbols as a rule for manipulating them in equations. Geometry examines properties and shapes, right? This could be just a cube of copper on your desk, or it could be the shape of the universe. Calculus investigates rates of change and accumulation, right, including differentiation and integration. So physicists use calculus a lot because we like to see how things change in time. So we have these time derivatives, which lets us, we can use them to predict what's going to happen in future times. There's probability and statistics. So we'll look a little bit at these when we go to examine just how our assessments are scored, right? So this would talk about things like averages and the likelihood of something to happen. There's number theory that looks at the properties and relationships of all the different types of numbers. Discrete mathematics functions on objects that are discrete and separate. So for example, when you record music on your computer, you actually don't control, you actually don't record all of the sound. What really happens is your computer at specified time intervals will take a little recording, right? So this is discretely done as opposed to being an analog process. We also have applied mathematics, which takes all of these forms of mathematics and tries to apply them in areas of physics and engineering and all the other sciences. And finally, we have engineering. So engineering is the application of scientific principles and mathematical methods and empirical evidence to design and create and build and maintain and improve structures and machines and to build things. Sometimes the line between all of these different areas, STEM areas, are not very solid. So for instance, the line between engineering and physics can become blurred sometimes. So for instance, our most of our courses at Stockton are applied physics courses. So we look more at how we're going to apply the laws we have that we have in physics to everyday problems. So some of the key aspects of engineering is number one, they do problem solving, right? So they find something wrong and they try to fix it. They try to design new products, right? And come up with innovations. So maybe a light bulb that doesn't cost as much electricity, right? And is more efficient. Usually they're interdisciplinary collaborations, right, between various fields such as science and architects and designers and business. There's many specialized fields. So there's civil engineering and mechanical engineering and electrical and chemical and aerospace. And once again, these aren't always clearly defined. So for instance, a civil engineer might have to talk to a structural engineer and when building a bridge. They also look at implementation. So once there's engineers that once they come up with a good idea, they find the most efficient way to have it implemented. Engineers also like to optimize, right? So they increase the performance and try to, for example, save you money by saving you saving on your electric bill. So we said that science follows the scientific method. So sometimes it feels like this, right? We have that eureka moment, then we go to the lab and it doesn't quite work. And then we just give up and we think nothing's good and the universe is broken and science is a lie. And then all of a sudden we realize, oh, I forgot to do this. And then we have the eureka moment and it keeps going around like this. So I know it feels like that sometimes, but really here's the real scientific method. So in essence, we ask a question. So we've observed the universe and we ask a question. And then we do some background research. And then we construct a hypothesis. And then we test it with experiments. and then analyze the results and draw conclusions. And then if the hypothesis is true, we report it. And if the hypothesis is false or partially true, then we go back and try again. The one difference is that that this diagram doesn't show is there should be a line from reporting results to doing basic research. So we have to keep testing these results, right, and seeing if they're correct. So another way of saying it is that we observe nature or the universe, then we ask a question about it, and then we research and come up with a hypothesis, and then experiment and test the hypothesis, draw conclusions, and once again report. One thing about science is that science isn't there to find the truth, or really what we do is we love to make models. We look at the universe and the world around us, and we try to model it to make predictions. So there's different types of models we use. So a model is not an exact copy. It's a representation of some aspect of real things. So if you ask most scientists, there's 3 types of models, but in atmospheric physics, we actually use, and meteorology, we use really 4 types of models. So the first type is a physical model. The second type is a mathematical model, a conceptual model, and a graphical model. So physical models. So physical models are models that you can see and touch, and these are called physical models. And they show how parts relate to one another, and they show how things appear when they change their position or how they react to outside forces on them. So here's some examples. One, here's a little model of our universe. I'm sorry, of our solar system, not universe. So here's the sun and the moon's out there, and there's Saturn you can recognize. And what this model does is has a set of gears in there, and as the day changes, you can see as the time changes, you can see the planets revolve around the sun. A globe is another model, right? It's not an exact representation, but it gives us an idea of what it actually looks like. Or for example, here's a model of a human torso, right? So it's not an exact copy, it's a model of how things work. Most of my research is in atmospheric physics and astrophysics and meteorology. And physical models are a little tough for us, right? We can't make a little town with a little hurricane going through, right? Or a little tornado whipping around, right? So some good examples in science that you may be familiar with physical models are, for instance, these models for molecules that are used in chemistry, right? So from them, you can see how bonds are formed and things like that, but they're not an exact model of what the molecule actually looks like. Here, we see this is a chamber that some atmospheric physicists use to try to represent a tornado and to see what the processes are to create this tornado. And it's really a pretty poor substitute for what an actual tornado looks like. So physical models are sometimes hard to use. We also have conceptual models. So conceptual models make comparison with familiar things to help illustrate or explain an idea. And conceptual models can be a system of ideas, And the classification of systems can be used to classify living things, for example, right? This is a conceptual model. So in classification systems, scientists group organisms by similarity. So for example, the Bohr atom, where we have protons and neutrons surrounded by these electrons that are orbiting around, right? This is a conceptual model. This is not exactly what the atom looks like. However, it's very useful for when, once again, we're looking at chemistry and trying to find out how things bond and things like that. So the atom is definitely not tiny little dots that are positive and neutral and negative, and the negative ones are flying around, orbiting like planets around the nucleus. However, it's a very useful model, and it gives you a picture in the head. It puts a picture in your head of how they work. In weather, a good conceptual model is called the Norwegian cyclone model, and it explains how most of the really bad storms happen up in the mid-latitudes where we live. So what happens in this model is that we have a stationary front. So maybe there's cold air up in Canada and warm air down in the United States. And the wind blows in different directions on each side. And what happens is this becomes a warm and a cold front. And the cold front moves much faster than the warm front, and it pushes the warm front up into the air and creates clouds. And here's one of the storms, one of our nor'easters, as it hits the coast of New Jersey. So once again, this is a conceptual model. It doesn't actually predict anything. Like, for instance, I can't use this model to say it's going to rain tomorrow. But what it does is it helps us understand exactly what's going on in this system. Just like the Bohr atom doesn't exactly represent the atom, but it gives us an idea of how it works. We also have mathematical or numerical models. So now that we have strong computers that are really fast, what we can do is create computer models and save a lot on the experimentation. Right? So these are simple mathematical models that allow you to change things as many as how many miles per hour a car can go. And these are mathematical models that are run on a computer. And some examples are trajectory equations and weather models and climate models. So you use a numerical model all the time, or a mathematical model. So for example, if you average 30 miles per hour in your car, how far can you go in 3 hours? Well, it's 30 miles per hour. We're going to go for 3 hours. It looks like it's 90 miles. So if in your head you answered 90 miles, what you did was use a mathematical model. So you said that the distance is equal to the speed times the time. We like to write it with symbols. So the triangles are called delta, and that means change. And X is our position. V is for speed or velocity. The difference is speed is just a magnitude, how fast you're going, and velocity includes a direction. So if you're going 60 miles per hour north, that would be a velocity. So here's an a numerical model that you use all the time without even thinking about it. The models we use in weather models, or the equations we use in weather models, are much more complicated. So for example, they include these force equations This is actually acceleration. So it's force divided by mass. And we use forces such as the gravitational force and the pressure gradient force. And we have to keep account of energy. So we have the energy coming in from the sun, and the energy from the sun creates all of the weather that we have. If there wasn't something called differential heating from the sun, we wouldn't have any weather. So what happens? The sun bears down pretty directly on the equator, and it gets really hot there. And then the sunlight is less direct up in the North and South Pole, so it stays cold there, and that's what starts everything. And then the Earth begins to spin, and we get complications like this. So we had physical models. These are reduced sized or scaled down versions of the real thing. So for example, when you go into the physics lab and study electric motors, we'll have a model of a little electric motor, right? And it's scaled down from what a real motor looks like. Then there were conceptual models. So these are used to give you an idea of what things look like, right? So we said, for example, our model of the solar system, right, gives us an idea of what the solar system looks like. Then we had numerical models or mathematical models. And these are just equations that we use to model processes that go on in our everyday life. And then I said, as we said, atmospheric physicists and meteorologists, we like to add in one other kind, and that's a graphical model. So here shows the rain and wind and pressure across the United States, right? And really, we've only have a couple of data stations, and we collect that data and then come up with this graphical model of what's really going on. So what I'm saying is, here it says, for instance, that that the pressure is 1,000 millibars, and it's 1,000 millibars. We'd say it's 1,000 millibars all along here. Well, we didn't measure every one of these points to find out what it was. So this is really a model. It's not exactly what happens. It's what we infer from the data that we have. So I'm going to talk a little bit about modeling. And the first thing I want to remind you is that you won't be tested on the mathematics. So don't get lost in that. Just try to follow along if you're not very good at math or if you haven't had much math, right? And see if you can get the idea of what we're doing with these models. So first, there's qualitative models, and these are relating to or measuring or measured the quality of something rather than its quantity. And I'll explain what that means in a second. And here's quantitative. That's relating to or measuring or measured by a quantity of something rather than its quality. So I want an exact value, right? So for example, here's about roughly 200 years of data. And what it is the average yearly temperature, the maximum yearly temperature, and the minimum yearly temperature. And as you see, so in essence, this should be summer, and this should be winter. But as you know, sometimes we have warmer winters and sometimes, we have hotter summers and sometimes less hot summers. Sometimes we have really, really cold winters like here, or we could have warmer winters. However, we're going to draw a straight line and assume it follows this linear trend. And what we find is that on the average, for example, in Japan, the temperature in the summer is going up about 0.01 0.07 degrees Celsius every year. Now, we can't use this equation to predict what the next summer will be. Sorry about that. We can't use this equation to predict how hot the next summer will be. All we can say is that as time goes on, it seems like the summers are getting a little warmer. So this is a qualitative model. I can't use, if you ask me to use this model to tell you what what next summer's temperatures will be like, I can't do it. But if you ask me over the next 100 years, how much warmer it will get, I can give you a rough idea, a rough estimate. So this is a qualitative model. Now here's that same information, and these are monthly average temperatures. And here's an equation that predicts them. And this still only gives us an approximation, but it's getting a little more quantitative. So I can use this equation to predict what the next month's temperature will be, right? It won't be perfect, and I might be a little off, but I can use it to find out. And we have equations such as if we drop a ball, we have this nice equation that fits the data. And what scientists, especially physicists, try to do is come up with equations, and you say, where will the ball be next? And I can tell you. And you say, where will it be in 10 seconds from now? And I can tell you. So the idea is we come up with these numerical models that try to predict what's going to happen. So when we build these models, we like to do, we go through a couple of steps. The first is to clearly state the assumptions that the model is based on. And two, completely describe the variables and the parameters. The parameters are variables that don't change once you start the problem. Okay? And finally, we want to use assumptions formulated in 1 and 2 to derive equations. So we have different kinds of variables and parameters. There's independent variables. A good independent variable is time. Time will go on and go on and go on, and there's nothing we can do about it, right? So time just continues to march forward. Then there's dependent variables. So for instance, the temperature in New Jersey depends on time. In the summer, it's hot. In the winter, it's cold. And parameters don't change with time once you have started the problem. So for instance, a parameter is how fast or the rate at which the velocity of a ball increases as it approaches the Earth. So that's known as gravity, right? And it's equal to G is minus 9.8 meters per second squared. That's the acceleration due to gravity. Okay, so let's look at population growth. So I'm going to create a model that suggests, that predicts what the population will be. So I'm going to say that the population is only proportional to the population. I'm sorry, the rate of growth of population is only dependent on the population. So this is what I'm saying. If there's 10 people, right, and they get married and have babies, right, and everything's great, but the number of children that are born per year is going to be a lot less than if there were 100 people. And if it's even going, and it's going to be, it'll be even greater, that be more children born each year if there's 2 million people. So what we're saying is that the rate of growth of population, in essence, how many babies are born each year, will depend on how many people there are there. I don't know, this sounds like a reasonable idea, at least at first, right? So we're going to say that the rate of population, so how fast the number of people that are being born depends on the population. So our independent variable is going to be time, and our dependent variables will be population, and then the rate at which the population is growing. So how many babies are being born? So we write how many babies that are being born as dp dt, right? So the more children that are born each year, the greater this will be. And the population is just the number of people. And there's some constant, and we have to figure out what the constant is. So I'm going to tell you, the equation we developed looks like this. And if you've had calculus, you know this means the time rate change of population is equal to a constant times the population. So let's tell you how we do. If I go ahead and look at Atlantic City, and I use my model to try to predict what's happening. So these are actual numbers of the population, and starting at 1860 up to 2014. Okay. And what I have shown here is from 1860 to 1910. And I'm going to model this with an equation. So here's my equation. You don't have to worry about that too much, but here's what it predicts. And it didn't predict exactly the numbers that I needed, but it did a pretty good job. So I've created this model, and that was my job as a scientist. And now I'm going to use it to predict the population, and it looks like we can do it. There's a little problem. We have to keep testing our equations, our models, right? We have to keep looking at the science. So from 1860 to about 1910, it looks like this model did really well. And once again, the model, the idea is for this blue line to touch all of these points. So, for instance, in 1890, there was about 12,000, I'm sorry, 120,000 people. And in 1910, there was almost 40,000 people. So everything's great, right? So we come up with this model and we predict what the population is in Atlantic City. And then we keep testing it. And all of a sudden, something went wrong. So the model, which was working very well at the beginning, all of a sudden, the population started to level out. So our model wasn't perfect. So what we'll do is go back and fix the model. Or we might have to throw the model out. Maybe it can't be fixed. So it seemed to work till about 1910, and then some stuff happened. Okay. So what happened? Well, here's some possible explanations. By the way, once again, what we would do as scientists is go back and try to fix this, right? So possibly what could have happened is we just ran out of room, right? There was just no more room for people, okay? And what we can do is correct our model to include the limit of resources, right? So if you're interested in something like this, take a differential equations course and we'll talk all about these different things. But anyway, just to close things up, why did our model fail? It's kind of interesting, right? Once was because in the 1920s, tourism was at its peak, and this was like Atlantic City's golden age. Also, during Prohibition, which was acted in 1919 and lasted till 1933, it was pretty much ignored in Atlantic City. So lots of people came there, right? And then after World War II, right, Atlantic City became plagued with poverty and corruption, and there was an economic decline. Also, another thing that happened was that in 1976, they passed a referendum approving casinos for Atlantic City, right? So this changed the landscape, right? So all those places that were beachfront homes were now giant casinos, right? Which affected the population. So anyway, the important thing to remember out of this is that the idea is that we look at data, we try to come up with a model, and that's usually an equation. And once we have that model, we see if it works. And it looks like this model did work at first. And then we keep testing it, and we notice that all of a sudden it starts to fail. And then we have to go back and fix it. All right, so this was an introduction to science and what the STEM fields are. And don't forget, the whole idea of this course is to look at how students in the STEM fields are tested. So before we find out or assessed, before we talked about how they were assessed, we should tell you exactly what they do and what we will be assessing. All right, so thank you, and we'll talk soon.